Hi, I'm Justin Cowart. I'm a fifth-year grad student at Stony Brook University, and today I'm going to be talking about my work studying Martian highlands bedrock plains using thermal infrared spectroscopy. The elevator pitch of this project is that we can use repeat thermal imaging of the surface at different times of day to separate the bulk composition of bedrock, which may reflect an eruptive, depositional, or alteration history, from that of regolith, which may reflect more modern weathering or grain transport processes. We can also separate these components even when they are not individually resolved at the imaging scale of our instrumentation. I'm applying this technique to intercrater bedrock plains, which are large thermophysically distinctive regions corresponding to increased exposure of intact rock. At left is a THEMIS daytime thermal infrared image of the surface, and in this image, rock-dominated surfaces appear dark. In contrast, regolith-dominated surfaces appear bright. My previous work mapped out and characterized these surfaces, looking at their morphological and spectral properties. Based on our characterization of these surfaces, we interpreted many bedrock plains as plastic deposits. The panel at right shows CTX visible light imagery of various bedrock plain surfaces. These surfaces typically are dominated by erosional landforms such as scalloped ledges, buttes, and periodic bedrock ridges. We also see that small craters are rare, suggesting that erosion is occurring faster than the rate of new impact crater generation. These properties are best explained if bedrock plain surfaces are composed of mechanically weak, easily eroded materials. To show this point in a little more detail, here's a comparison of two different points on the Martian surface. On the left is a high-rise image of a Terracebea bedrock plain showing good exposure of rock, the development of periodic bedrock ridges, and a small crater that has been nearly erased by erosion. On the right, we have a high-rise image at the same scale of a lava flow in Hesperia planum. Here we can see that small craters follow a fractal scaling. These craters also show good preservation of topography, and we see very little erosional development. Most of the surface also appears to be covered with regolith, suggesting that erosion is very slow. An interesting thing about bedrock plains is that they are commonly associated with spectral detections of the mineral olivine. Here, I am overlaying a visible near-infrared olivine parameter map from PRISM over the top of the thermal infrared image of the bedrock plain that I showed you earlier. We can see that the olivine signal is closely associated with bedrock exposure. When we compare the bedrock materials to the surrounding non-bedrock materials, we see that the bedrock has 5 to 10% higher spectral abundance of olivine. However, the signal isn't evenly distributed. These two stars show the locations of two high-rise images that I'm going to show in the next slide. The strength of olivine detections appears to vary with the amount of sand present on the surface. In this high-rise image, we can see the portion of the bedrock plain in the previous slide which did not have a CRISM olivine parameter detection. Sand is present but covers very little of the surface. In contrast, where we see a strong CRISM olivine parameter detection, sand covers much more of the surface. These regions also tend to correspond to higher amounts of olivine in the thermal infrared. The reason for this difference may be because in the visible and near infrared, the weak spectral features of olivine are most easily detected in fine particulate matter, such as sand. In the thermal infrared, the signal strength is strongly dependent on temperature. And the higher temperature of sand at imaging time may increase the visibility of minerals that are present in the sand. Bedrock olivine abundance also appears to be related to erosional processes. We performed a qualitative assessment of surface erosion, visually comparing small crater density and development of erosional landforms. We saw that what appeared to be more highly eroded surfaces had higher olivine abundance. This led us to hypothesize that olivine was being eroded out of bedrock and concentrated on the surface as a lag deposit due to its higher density and hardness. We weren't able to investigate this hypothesis in more detail due to the sparse coverage of high-resolution datasets, such as HiRISE or CRISM, that would have allowed us to follow up more closely. The source of the olivine signal strongly influences geologic interpretation of the bedrock plain's origins. Olivine is a reactive volcanic mineral that breaks down over geologically short timescales when exposed to water in the near-surface environment. So, if the olivine signal originates from bedrock, this would imply that the bedrock is pyroclastic in origin. This is because the generation and preservation of large amounts of olivine-rich clastic sedimentary infill from the surrounding olivine-poor highlands lithology is unlikely. However, if the regolith is the source of the olivine signal, then the generation of lag deposits through the deep erosion of olivine-poor clastic sedimentary infill may explain the observed olivine abundances. For this study, we looked at bedrock plains in the Terracebea region. These bedrock plains cluster densely in the highlands northwest of the Hellas Basin. They show among the highest olivine abundances observed in our global survey, and several show strong evidence for fluvial deposition or reworking of materials. We wanted to understand the petrologic origin of these bedrock plains. As a point of comparison, we also studied the Nili-Fosse olivine carbonate plain, given the strong evidence for pyroclastic emplacement of this unit. Our approach takes advantage of the differing thermal properties of loose sediment and rock. These materials change temperatures at different rates. All other things being equal, a surface at a higher temperature will contribute more to the spectral signal than a surface at a lower temperature. Thermal inertia is the measure of energy needed to change the temperature of a material. Over the diurnal cycle, a low thermal inertia material such as sediment will warm up more quickly and reach a higher temperature peak than a high thermal inertia material like rock. If we collect the thermal emission spectrum of a surface in the early afternoon, the sediment component will still be much warmer than the rock component and thus contribute more strongly to the spectrum. However, in the early evening, this thermal contrast reverses and the rock becomes the more dominant spectral component. This graph shows thermal modeling of the surface for two different THEMIS observations, one taken in the mid-afternoon, shown in red, and one taken in the early evening, shown in black. These thermal models take into account the location, time of day, season, and dust opacity at the time of each THEMIS observation. This model outputs the expected thermal radiances at THEMIS band 3 for a range of materials with varying thermal inertias. Here we're comparing the expected radiances for a 200 micron sand and a clastic rock similar to one measured in the Columbia Hills by the Spirit rover. In the mid-afternoon observation, the sediment component has approximately 20% higher radiance than the clastic rock component. This means that it will contribute 20% more per unit area to the observed surface spectrum. As the temperature contrast reverses in the early evening, sediment fades relative to clastic rock. In this observation, sediment is 26% less bright than the clastic rock. This means that it will contribute 26% less per unit area to the observed surface spectrum. Here are the THEMIS observations corresponding to the thermal models seen on the previous slide. These false color images show relative differences in silica content, with yellow and green areas being more silica rich and purple areas being more silica poor. We see large changes in colors between the afternoon and evening images, suggesting that we're seeing different components in each image. The 8 to 12 micron region of the spectrum observed by THEMIS is largely representative of silicate mineralogy. Silicate absorption minima in this region are controlled by silica oxygen stretching. More highly polymerized silicate minerals, such as quartz, will have an absorption minimum at shorter wavelengths. Less highly polymerized silicate minerals, such as olivine, will have an absorption at longer wavelengths. THEMIS does not have the spectral resolution to identify specific silicate minerals. However, we can see changes in bulk silica. The figure at left shows a series of reference spectra with decreasing silica content. We can see that the emissivity minimum shifts towards longer wavelengths with decreasing silica. As a result, if sediment and bedrock have different compositions, we should see the position of the emissivity minimum shift between daytime and evening images. The direction of the shift will depend on the difference in silica content. I'm using the cubic spline fitting method to quantify the position of the emissivity minimum. This method fits a cubic spline to an observed THEMIS spectrum, and the minimum value of this function occurs at the approximate wavelength of the emissivity band center. This process is shown in the figure at left. Here's what we would expect to see in terms of locating the source of the olivine signal in bedrock plains. If the olivine signal is originating from bedrock, we would expect to see the evening emissivity minimum shift to longer wavelengths relative to the afternoon minimum, or to its right. If the olivine signal is originating from regolith, we should see the evening emissivity minimum shift to shorter wavelengths relative to the afternoon minimum, or to its left. At left is a figure showing bedrock plane spectra pulled from the same location using the two THEMIS observations I showed you earlier. We can see that the emissivity minimum of the evening image is at shorter wavelengths relative to the afternoon image. This tells us that the olivine signal is likely originating from regolith. This slide shows daytime over evening spectra for all bedrock planes for which daytime and evening image pairs were available. These ratio spectra were a way to make sense of the spectral trends we observed in these bedrock planes. We see that they fall into one of four groups. These ratio spectra also provided a check to ensure that residual atmospheric features were not influencing interpretation of spectral trends seen in bedrock planes. Group 1 spectra have a ratio emissivity feature between 10 and 11 microns. This suggests that more olivine is present in the afternoon image. Group 2 spectra have relatively flat ratio emissivity spectra. This suggests that afternoon and evening spectra are not very different from one another. Group 3 spectra show ratio emissivity features between 8 and 10 microns. This suggests that the sediment cover has experienced olivine depletion or is more silica-rich than the underlying bedrock. Finally, Group 4 spectra show ratio emissivity spectra consistent with residual atmospheric features. Only one bedrock plane fell into this group, with the afternoon image showing strong water ice contamination. This slide shows all daytime-evening spectral pairs for Group 1 bedrock planes. We can see that in all cases, the evening emissivity minimum is at shorter wavelengths than the afternoon minimum. This suggests that the olivine signal in these bedrock planes is originating from Regolith. In addition, we can see that the shape of the evening bedrock plane spectrum also suggests that the bedrock contains more volcanic glass or alteration minerals than the regolith. Afternoon-evening image pairs in Group 2 spectra show very little change in shape. For the two bedrock planes in the top row, we see a large shift in the emissivity minimum position between the daytime and evening observations. The silicate emissivity feature in this region is relatively broad. This makes the cubic spline fit more sensitive to changes in spectral slope, so the changes that we see here probably are not significant. The relatively similar shape of the spectra in these three bedrock planes suggests that the regolith composition reflects that of the bedrock. Group 3 spectra indicate that the bedrock likely hosts more olivine than the regolith. In the Nili Fosse olivine carbonate plane, we see a clear shift in the emissivity minimum towards longer wavelengths. This is consistent with previous observations, which suggest that the regolith in the Nili Fosse region have lower olivine content. In bedrock plane SP15, the story is a little more complex. The emissivity minimum location does not change much between the afternoon and evening spectra. This would suggest that there's little difference between the bedrock and regolith. However, in the evening spectrum, we see that the emissivity minimum feature in the 10 to 11 micron region deepens. This indicates that olivine is present in higher abundance in the bedrock than the regolith. We also see that the emissivity feature deepens in the 8.5 micron region. This indicates that a more silicic mineral is also present. The presence of both olivine and a more silica-rich component effectively cancel each other out, leading to the small emissivity position change seen in the evening spectrum. The spectral trends observed in Group 3 may indicate a pyroclastic origin. Another possibility is that olivine is present in the regolith, but is fine-grained relative to the other components. Extremely fine olivine would have reduced spectral contrast, thus reducing its contribution to the overall spectrum. A final possibility is that the observed spectral trends indicate an alteration event. Olivine would be preferentially attacked in an aqueous alteration scenario, which may account for its removal in the regolith. So to conclude, I hope that I've shown that we can use repeat thermal imaging of the surface over the diurnal cycle to improve our understanding of surface geology. As THEMIS conducts an evening surface imaging campaign, this promises exciting new science for the instrument as it enters its 20th year of operation. The strong olivine signal in some bedrock planes appears to originate from regolith. Given the strong fluvial signal we see in some of these bedrock planes, it suggests that they are clastic sedimentary deposits. Other bedrock planes appear to have high amounts of bedrock-hosted olivine. These planes are likely pyroclastic in origin. I would like to thank all of the people listed below for their help in making this project possible, and thank you for watching.